Can you hear me?
Yes, sir.
Okay, so so what we were discussing yesterday. So yesterday we saw that limit of. So what we discussed yesterday. So if a is positive, then what is limit of a raised to 1 by n? What is this limit? Limit right? So what is limit n raised to 1 by n as n tends to infinity?
1.
1, right? If a is positive. Now if a is negative, right? Then what can you say about limit n tends to infinity a raised to 1 by n? What is the limit? Yes. Does it exist? Does it make sense? Suppose a is equal to -1. Then what is a raised to 1 by n? That means -1 raised to 1 by n. Does it make sense? Right? So this does not make sense because in particular if n is equal to 2, then what is -1 raised to 1 by 2? Root of -1 is not real number. Correct? So if a is negative, a raised to 1 by n as a sequence does not make sense. Right, so we can just think about if a is positive. Correct. So also we can see that if a is positive, then what is limit a raised to n? What is limit a raised to n? If a is positive, what is limit a raised to n?
Infinity if a is greater than 1.
If a is greater than 1, right?
And
0
0 for a between 0 and 1.
And 1 for a is equal to 1, right? What about negative?
It does not exist.
If a is equal to does not exist if a is equal to -1, but if a is equal to if -1 less than a less than 0, that means if a is here between -1 and 0, then what is limit? For example,
0.
a is equal to -half, right? And what is a raised to n? is minus half raised to n. That means minus 1 by 2 raised to n. Then what is this limit? As n tends to infinity, 0. So 0, and if a is less than minus 1, right? For example, a is equal to minus 3, does not exist, right? So in this way we can understand this. Anyway, so our this problem we yesterday we were talking about a raised to n upon n factorial. So let us simplify this problem and see what happens. For example, so xn is equal to, for example, 2 raised to n upon n factorial. Look at this sequence. That means what I am doing, I am replacing a by 2 for particular a, right? Then does this sequence converge? Does this sequence converge? And second question is what is limit if s? What is limit? Correct? So first observation for this sequence, xn 2 raised to n upon n factorial is greater equal 0 for all n. Is it correct?
Yes, sir.
So each term is greater equal 0. Next, so what is the second observation? What is xn plus 1? Xn plus 1 is 2 raised to n plus 1 upon n plus 1 factorial, right? So 2 raised to n into 2 upon n factorial into n plus 1. Is it correct? Whatever I have written is correct?
Yes, sir.
Yes, sir.
So 2 raised to n upon n factorial into 2 upon n plus 1. And this is basically xn into 2 upon n plus 1. Right? Now note that 2 upon n plus 1 is less than 1. Is it true? Less than or equal to 1?
Yes, sir.
Yes,
Yes.
right. So for all n greater equal 1. If n is equal to 1, it is true. In fact, 2 upon n plus 1 is strictly less than 1 if n is strictly greater than 1. That means for all n, basically this thing is less equal 1. Therefore, xn plus 1, which is xn times 2 upon n plus 1. Can I say that it is less equal xn?
Yes, sir.
Because bracket is less than or equal to 1. No doubt. So what we can conclude from this?
It is monotonically decreasing.
Right. So already xn is bounded below. Yes.
Yes, sir.
Why? So
It
because
is greater than 0.
so bounded below by 0. So already since xn is bounded below, we conclude that xn is convergent. Right. So the sequence converges, but what is the limit? Right. What is the limit of the sequence? So second question was what is limit? And how to see the limit? That particular number is a limit of this sequence. Right? Okay. Let us do some simple calculation and try to get something, some observations. So look at xn. Okay, I will start with simple case. Look, I will look at x3. Right? What is x3? What is x3?
2 to the power 3 by 3 factorial.
Very good. Right? So power is 3 and 3 factorial. So 2, 2, 2. What is denominator? 3, 2, 1. Right? So what I will do, I will just separate out these two things, that is 4 upon 2 and 2 by 3. I will separate this out. Right? 4 by 2. Correct? So okay. Now x4, what observation I want to make is this. What is x4? 2 to the power 4 upon 4 factorial. So 2 into 2 upon 2 into 1, that's is 4 by 2. That is fine. What are remaining factors? 2 upon 3, 2 upon 4. Right? Among which is larger one? Which is larger one among these two factors? Which is larger one?
2 by 3.
2 by 3. Right. But 2 by 3 is less than 1. Can I say that this quantity is less than 2 into 2 by 4? Yes.
Yes, sir.
Because 2 by
Yes,
3
sir.
is less than 1. X5, can I say that x5 is less than or equal to 2 into 2 upon 5?
Yes, sir.
Am I right? Because
Yes.
x5 is what? 2 to the power 5 upon 5 factorial, which is uh, 2 into 2 upon 2 into 1. That is okay, because why I am separating out this factor? What is your guess? Why I am separating out this factor? Why I am separating out the first factor? What is your guess? Yes. Yes, what is your guess? Every time 4 upon 2, this factor is greater than 1 and it can be taken away, and the remaining factors are less than 1. Right? So only this factor is greater than 1 and all these factors are less than 1. Correct? So can I say that this is less than 2 up into 2 by 5, because 2 by 3 is less than 1, 2 by 4 is less than 1, and I will put 2 by 5 as it is. So is it correct now?
Yes, sir.
Yes, sir.
Now I want to generalize this. Xn 2 to the power n upon n factorial. What is it? 2, 2, 2. How many times 2? How many times?
N times.
N times. Correct. Then what is the denominator? 1 into 2 into 3 into up to n. This is denominator. So n factorial. Now I will separate out something. How many numbers are in the denominator and how many numbers are in the numerator? N, correct?
N.
So I will pair 2 upon 1, then 2 upon 2, then 2 upon 3, 2 upon 4, up to 2 upon n. Here I am assuming that n is greater than 2. I am assuming that n is greater than 2 because anyway smaller n are not uh, we don't want to worry about smaller n because we want to see what happens at infinity. Fine. Now in this last expression, what is your observation? How many factors I found here? How
N.
many? N
N
factors.
factors.
Now you tell me what is your observation from these factors. First factor, second factor are greater than or 1 or greater equal 1, right?
Yes, sir.
And remaining factors are less than 1, right? So therefore, if I write first factor which is as it is, so what is first two factors? 2 raised to 2 upon 2 factorial as it is every time, that is 4 by 2, and then this third factor is less than 1, fourth factor is less than 1, so I will replace this all these remaining factors by 1 except last one which is 2 by n as it is. This amount is what? Is it
Greater than.
Greater.
right? Greater than the previous one, right? Or no harm in saying that less equal, no problem. So ultimately what I get? 2 into 2 upon n. So therefore what we get? What is the conclusion? Therefore xn is less than or equal to 4 upon n for all n greater equal 3. Yes,
Yes, sir.
correct. And already we know that all terms are greater equal 0. So by sandwich principle, what is limit of xn?
0.
0.
Right. Limit of xn must be 0 and therefore we found limit. So is it clear? Proof is clear.
Yes, sir.
And then how did I decide my strategy? Because I observed something from x3, x4, x5 and I found that key this 4 upon 2 can be separated, which is a fixed number every time, but the remaining factors are less than 1. That may help us. So that I observed and then I decided my strategy. Right? Okay, now I will give a sequence 10 raised to n upon 10 factorial, n factorial. And you work out same, so prove that. Limit of xn is 0. What will be the difference now in previous example and this example? What would be the difference?
The
So the
terms would
common
be
one,
less than 1.
Yeah, here if you observe that key 2 upon 1, 2 upon 2. But in this case 2 is replaced by 10 and xn is less than 4 upon n after 2. What will be here then?
After 10.
After 10, right? 10 plays important role here, right? So now you understand what is the crux. Now, if I look at sequence xn, a upon a raised to n upon n factorial, provided a is positive. Now, can you generalize the same idea now? Yes.
Yes, sir.
Right. So what is the crux here? Xn is less than what? Xn is less than what?
A square by n.
Uh, no, because A can be 2, 3, whatever it may be. Right? So, what about here? What about 10 raised to n upon n factorial? What is it? 10 upon 1, 10 upon 2, 10 upon 9, no problem. 10 upon 10, still no problem. But after that, 10 upon 11, 10 upon 12. Here the process starts. The factors are less than 1. And therefore, which term will be common every time? Like in previous case, 2 raised to 2 upon 2 factorial was common. Right? So 10 raised to 10 upon what? 10 factorial. And what is the remaining now? Remaining everything is all factors are less than 1. So therefore in this case xn is less than 10 raised to 10 upon 10 factorial into what? Into
N by
10,
n.
10 upon n plus 1 for n greater than or equal to 11. And 10 raised to n, 10 upon 10 factorial is a constant, whatever its value. Anytime this is a constant number, and therefore as n tends to infinity, this tends to 0, so limit of xn is 0.
So why n plus 1?
Uh, observe the previous situation. N, you want to say n, right?
Yes, sir.
N, right. So it should be n, correct? Then as n tends to infinity, limit is 0. This is what if you compare the previous problem and this. And therefore, if you have general A, then what is the general proof?
Xn would be less than a raised to a upon a factorial into a by n.
Uh, okay, then you have to look at what is the integer. So there exists some n, right? So choose let natural number n greater than a. Choose natural number a greater than a. Correct? Choose
Yes.
does there exist natural number greater than a?
Yes, sir.
Yes.
So choose any one of them, no problem. Then xn is less than a raised to n upon n factorial into a upon n. Am I right? For n greater than n. This particular n. Is it correct now?
Yes, sir.
Yes, sir.
So no doubt, no ambiguity in this now.
No, sir.
So and if you have still confusion, you can try for a is equal to suppose 4.7. Try for this.
Sir, sir, can't it be like a raised to a, no?
But
Like
in
we did in the previous cases.
previous case 10 2 were natural numbers integers, but a may not be integer,
Yes, sir. Okay.
right? So see, when we solve some general problem, you should think about worst to the worst possible situation. Then your proof is clean and clear, right?
Like you've taken a raised to n by n factorial, no? So it can be less than 1 also.
Yes,
This.
no problem. No problem. But in any situation, we can find n which is greater than a, and for such n this is certainly true.
But sir, then this n is also not true, no? That small n you have taken, a by n. Like it is not always less than 1.
No, what is your a? What is your a? Suppose you take a is equal to 1 by uh, 15. Then what is xn? A raised to n upon n factorial. That is 1 upon 15 raised to n into n factorial. And no doubt this sequence converges to 0.
Yes, sir.
Right? Suppose a is equal to 4.7. I will take natural number n is equal to 5, which is greater than a, or 6, no problem, you choose any one of them. Then look at xn, a to the power n upon n factorial, right? So this is less than or equal to 5 to the power n upon n factorial,
Yes, sir.
because my 5 is greater than a and a is 4.7, right? And this is less than or equal to 5 to the power 5 upon 5 factorial into 5 upon n for n greater than or equal to 6.
Okay. Yes, sir.
Right? Now is it clear? No doubt.
Yes, sir. Okay.
And therefore, whatever I have written in this red box, this red box is important. For any a, this is a general way. Yes. Whatever a positive as you select, there is a natural number and you choose a natural number greater than a. From that you can understand something. No, here some modification is needed. What modification? What modification is needed? Yes, n upon n. Right,
Yes, sir.
correct. So you think about it, and our problem was 2 raised to n upon n factorial, then 10 raised to n upon n factorial. You work out same problem for 5 raised to n upon 5 factorial, and for general a raised to n upon n factorial. This problem we reduced to for integer n, and then same strategy.
So when a is only like a natural number, so no real number, then the previous one is valid, no? Like a raised to a by n factorial that day.
Right? That, see, you have to use your sense. Key, what whichever is convenient without violating any rule. How can you prove that it is less than or limit is 0? Right?
Okay.
This is not the only technique. This is what I easily naturally comes. There are other techniques also that we'll see later. Right? Same
Yes.
sequence, same problem we'll treat with some different technique. And what is that technique? So let us see this theorem. Same problem we'll treat by some different technique. And believe that there is not a unique technique. Whatever I am saying is not the only way. You may find some different ways. Right? So let xn be a sequence of positive real numbers. So all xn's are positive. That means no number is 0 or negative. Let L is equal to limit of xn plus 1 upon xn exist so if L is less than 1, then xn is convergent and limit of xn is 0. If L is greater than 1, then xn diverges. Right, so read the statement carefully. Read the statement of theorem carefully. So, for example, what is given? Suppose I am given some sequence xn is equal to n raised to n upon n factorial. Suppose this is my sequence. Then what is xn plus 1 upon xn? This is new sequence. I am dividing the next term by previous term. What is xn plus 1? What is xn plus 1? N plus 1 raised to n plus 1 upon n plus 1 factorial. This is xn plus 1 upon xn. What is xn? Can you see the green color? Whatever I have written in green color. Can you see it?
Yes, sir.
Okay. Now simplify this. So n plus raised to n into n plus 1 divided by n plus 1 into n factorial, and denominator is n factorial upon n raised to n. Right, so this n factorial cancels with this n factorial, this n plus 1 cancels with this n plus 1. What remains? N plus 1 raised to n upon n raised to n. So this is a new sequence. This is a new sequence. Now what is limit?
1.
What is limit? Limit xn plus 1 upon xn. This is what in the statement L. So limit n tends to infinity, but xn plus 1 upon xn we have calculated it as it is. What is it? You check the calculation whether I am making mistake or what is it. What is it? N plus 1 raised to n upon n raised to n. Is it same as n plus 1 upon n whole raised to n? Is it correct?
Yes.
Yes, sir.
Yes, sir.
Now you tell me what is limit. What is limit? You know the limit actually.
Oh, it's E.
0.
It's E. No, it's E. Euler.
Is it
It's
same as
Euler's. Yes, sir.
yes?
So the limit will be E.
E, which is greater than 1. Right? And therefore from above theorem what you can conclude? Limit of xn plus 1 upon xn is E. And therefore what is the conclusion of above theorem? If limit is greater than 1, then sequence is divergent. Xn is divergent. Xn plus 1 upon xn is something new, different sequence. Its limit is E, which is greater than 1. So what about sequence xn? Observe the
It is divergent.
Divergent.
sequence is divergent. If this limit comes out to be greater than 1, then original sequence is divergent. Therefore, xn is divergent. Right. So, do you understand now the meaning of the statement? Right.
Yes,
So,
sir.
we'll discuss the proof also. Okay, so xn is divergent, correct? But if you look at sequence yn, which is n factorial upon n raised to n, I am looking at some different sequence. Then what is yn plus 1 upon yn? What is yn plus 1 upon yn? I am looking at some different. This is not same as xn. Is it? Do you understand? Yn is not same as the xn.
Yes, sir.
Yes, sir.
So what is yn plus 1 upon yn? Just do the similar calculations as we did before. And is it same as n raised to n upon n plus 1 raised to n? You check it. Right? And now what is limit of yn plus 1 upon yn? It is just inverse of the previous one. 1 by e, which is less than 1. You check all the calculations. Now what is the conclusion?
Convergent sequence.
Xn is convergent.
Yn is convergent. And more, what is the limit? The statement of theorem.
0.
0. Okay, so this is how the statement, this theorem is important. Now let us see the proof. Right, so how to prove it? How to start the proof? Okay, what is given? Given that L is equal to limit of xn plus 1 upon xn. Xn plus 1 upon xn is a new sequence, right? Which is constructed using the sequence xn. Right, so suppose L is less than 1. Right, so can L be negative? Can L negative?
No,
No, why?
because xn is a sequence of positive real numbers.
Right, and therefore xn plus 1 upon xn are also positive numbers, and therefore limit of this xn plus 1 upon xn cannot be negative because all xn plus 1 upon xn are positive. Right, so L cannot be negative, therefore L is in between 0 and 1. Right, now let us choose some number alpha between L and 1. So let R be a real number such that L less than alpha. Okay, alpha, we want to select alpha here. So let alpha be a real number such that L less than alpha less than 1. Can you produce such number? Is it possible?
Yes, sir.
Yes, because L is less than 1, there is some gap space between L and 1. In that space, there are many numbers. Choose one of them, alpha. Right. Therefore, uh, alpha minus L, is it positive?
Yes, sir.
Right. Now, what is assumption since limit of xn plus 1 upon xn, this is a new sequence, is L by definition of limit there exists k such that what? Limit of something is L, and by definition of limit, for epsilon is equal to alpha minus L, which is a positive quantity, there exists k such that what?
Distance between x l and xn plus 1 upon x is less than epsilon.
Less than epsilon for all n greater equal k, because we are talking about limit of xn plus 1 upon xn. Or you may, if you want to be more comfortable, you can say yn is equal to xn plus 1 upon xn. This could be a new sequence, and then you can say that limit of yn is L, and then you apply definition to yn. That could be the another way, but now you can understand xn plus 1 upon xn itself is a sequence, right? So therefore what? Minus epsilon less than xn plus 1 upon xn is less, minus L is less than epsilon for all n greater equal k, right? That means, but what is epsilon? What is epsilon?
Alpha minus L.
Right, because we have chosen some epsilon. For every epsilon there is k. In particular for this epsilon also there is k.
That should be L minus alpha, right? The LHS, because it's minus epsilon.
on left side. Right? Is it correct now?
Yes.
Okay.
Yes, sir.
Therefore, xn plus 1 upon xn is less than alpha minus L plus L for all n greater equal k. So forget about left hand side, just what is right hand side says. Right? So xn plus 1 upon xn is less than alpha for all n greater equal k. That means xn plus 1 is less than alpha times xn for all n greater equal k. Correct? So in particular, what about xn, xk? N is equal to k. I am taking n is equal to this fix. K is a particular number. So suppose for n is equal to k, is it true that 1 is less than alpha times xk? Is it true?
Yes, sir.
Fine. So what about xk plus 2? I will look at next now. N is equal to k plus 1. Right? So x1, x2 and xk. This is a particular term. After that this is true. K less than epsilon, all these things. Xk plus 1 and so on. Now if n is equal to k, I found that xk plus 1 is less than alpha times xk. Now I am looking at xk plus 2. Is it less than alpha times xk plus 1? Is it true?
Yes,
Yes,
sir.
sir.
Yes, sir.
But already by previous step, xk plus 1 is less than alpha times xk. So alpha as it is. And this xk plus 1 is less than what? Alpha times xk. Am I right? Which is
Yes.
xk. Now this xk is a fixed term. Whatever it is a number now. Xk is a number because it is a k term of sequence which is a fixed number. Right. Now what about xk plus 3? Can I say directly it is alpha raised to 3 into xk, which is a particular term. This term, particular term xk. This is a number now because if you say the particular 100 term, suppose k is equal to 100, then alpha xk plus 3 is less than alpha raised to 3 into x100. Right, and this is a number because it is a 100 term. Do you understand? In general, for n, okay, in general, before that, what about xk plus r? Xk plus 2, xk plus 3, xk plus r. Suppose r is 4. Can I say that it is alpha raised to 4 up into xk if r is 4?
Yes.
Right? By same logic. So, in general, what is it?
R.
R. Alpha raised to r. Right? So, now I want to generalize this. So, therefore, for n greater equal k. Now I choose. So here I choose. Here I choose uh, n is equal to k plus 1, n is equal to k plus 2, n is equal to k plus 3. Now for general n, what can you say about xn plus 1? What can you say about?
Less than alpha xn.
So it is less than alpha xn, but still further xn is less than alpha times xn minus 1.
Yes, sir.
Now continue this. Where we should stop? Where we should stop? Suppose k is equal to 10 and I choose n is equal to suppose 13. Then what about xn plus 1, that is x14 is less than alpha times x13 is less than alpha into alpha times x12 is less than alpha square into alpha times x11. Where we should stop?
X1.
No, how can you go beyond? Because we are sure about only for n greater equal k. We cannot go
Till
below.
xk.
We cannot go below xk, right? We cannot.
Yes, sir.
So here we should stop at. So this is less than x raised to 4 into x10 because k is 10. We are sure up to k, that is 10, but we don't know ki x10 is less than alpha times x9. We are not sure about this. Do you understand? What we are sure about? We are sure that xn plus 1 is less than alpha times xn for n greater or equal to k, not less than k. Yes, is it clear what I want to say? So where we should stop? We should stop at alpha raised to some power into xk because I am choosing n greater than k and go back, and we certainly we come to the xk. And then what is the power of alpha where we should stop? What
n
is
minus k plus 1.
Yeah.
You observe here, we started with x14 and we stop at alpha raised to 4 because our k was 10 in this case.
N
Right?
minus k.
Right. Suppose I start with n plus 1, then alpha raised to what? What is the power of alpha? 14 minus 10. That is the power of alpha. 14 minus 10 because k is 10. So what is power of alpha here? N plus 1 minus k. Yes.
Yes.
Right. Fine. Therefore, what is the conclusion? For n greater equal this particular k, xn plus 1 is less than alpha raised to n plus 1 minus k into xk. Xk is a constant now. Or I can simplify it further as alpha raised to n into alpha raised to minus k plus 1, no problem, xk, which I can further write it as some beta into alpha raised to n plus 1. What is beta? What is beta? Beta is a constant. And what is beta?
1 by alpha to the power k.
Xk upon alpha to the power k, which is a constant. It is not going to change whenever if you change your n. Am I right? Yes?
Yes.
Okay. Now we are at the crucial point. What is the limit? We are at the crucial point now. Therefore, 0 less than or equal to xn plus 1 is less than or equal to beta times alpha raised to n plus 1. And what is alpha? You go back. Where is your alpha? Where is alpha? Alpha is less than 1.
Yes,
Yes,
sir.
sir.
So, what? By sandwich principle. So, since what is limit n tends to infinity alpha raised to n plus 1? Alpha raised to n or alpha raised to n plus 1? No. Is it 0?
Yes, sir.
Why? Because alpha is less than 1, and therefore by sandwich principle, what is limit of xn plus 1?
0.
0. Can we say that limit of xn is 0?
Yes, sir.
Yes. Because n plus 1 and xn, the one step ahead, the destiny is same, limit is same, right?
Sir, can we directly prove that xn plus 1 is less than equal to xn for n greater than k? Then it would be a decreasing function sequence for n greater than equal to k. So the limit would be 0.
That is what we have used here actually, right? Because that
Did you use reduction?
sees the decreasing sequence doesn't mean that key limit is 0. You understand? Sequence is decreasing doesn't mean that limit is 0. If you look at
But
sequence
sir,
x,
it is bounded below also, no, sir? 0 at 0.
look at sequence xn is 1 plus 1 by n. This sequence is bounded below by 0. It is decreasing, but limit is not 0,
Yes, sir.
right? And therefore, when you make some argument, under what condition, under what situation the arguments are valid? Only decreasing and bounded below is not sufficient to say that that bound is limit, right? So there, here alpha plays an important role. Ki alpha controls, ki alpha push xn plus towards 0. Alpha raised to n this power push, right?
Yes, sir.
Because alpha raised to n tends to 0 and that push the xn plus 1 towards 0. So that is the main point, that the role of alpha is important. So second part, if L is greater than 1, L is greater than 1, then from this above proof, what you have, so if limit is greater than 1, then what happens? If L is greater than 1, if I choose suitable epsilon, then I can find that ki after some k all terms are here greater than L minus epsilon and L plus epsilon, which is a quantity still greater than 1, right? And then you think about the limit. So do you understand what I want to say? If L is greater than 1,
Yes, sir.
then if I choose epsilon is equal to, suppose what epsilon I should select now? What epsilon I should select? L1, and I want this epsilon, this distance. So epsilon is L minus 1 by 2. If I select this number as epsilon, half of the distance between L and 1, then this quantity is basically greater than 0, right? And if you, what is the importance of this? Ki L minus epsilon. What is this? L minus epsilon. L minus 1 by 2. What is it? 2L minus L plus 1. So it L plus 1. Smita Khandare, keep your mic off. See, you should keep your mic off if you are not talking with me, right? Okay, so if you choose this epsilon, then what will happen? There exists k such that xn plus 1 upon xn minus L is less than this epsilon. And then you see what happens. Then you will find that ki xn plus 1 upon xn minus L is less than epsilon greater than minus epsilon for all n greater equal k. N greater equal k. Right? And what does it mean? So what is minus epsilon? What is minus epsilon? What is minus epsilon? 1 minus L.
Minus L minus 1 by.
So 1 minus L by 2, right? Plus L is less than xn plus 1 upon xn is less than L minus 1 upon 2 plus L. I think our time is over. You just work out these calculations like previous one and see what happens. Then you will come across some situation like xn plus 1 is greater than some number a into xn, and this a is greater than 1 for n greater equal k, and we'll come to the situation like for n greater equal k, a raised to some n minus k plus 1 into xk, like similar to previous, right? And as a is greater than 1, as n tends to infinity, a raised to n minus k plus 1 tends to infinity, therefore xn tends to infinity. This is actually the point. But you just simplify the calculation and see. Next time we'll see some problems how to apply this technique to find limit. Alright, so is it clear?
Yes, sir.
Yes.
Okay, you think about it. Next time we'll see.